thank everybody for joining this session and also to my talk. And as was already mentioned, my name is Yury LYSOGORSKIY. I am from Ruhr University Bochum, or Interdisciplinary Center for Advanced Material Simulation, shortly ICAMS. And I would like to share our experience regarding data management for particular purpose, which is interatomic potential validation and development. And I hope you will enjoy it. So probably most of you know these diagrams about atomic simulations and its position in this simulation ladder with different time, length, scales, and disciplines. So we are mostly focused, at least in ICAMS, in maybe the first 3 or even 4. So we have 3 departments which deal with atomic simulations, microstructure modeling, macroscale modeling, and so on and so on. But my talk would be devoted exactly to electronic and atomistic world and simulation in this world. And the point under investigation here is how we can jump between these 2 steps, how we can go from electronic simulation, ab initio simulation to atomistic one, and how reliable these steps is. So I think all of you know that we have such kind of models which call interatomic potentials, which basically describe the interaction between atoms, ignoring the electronic degree of freedom, and that achieved by training the so-called, or maybe fitting the so-called potentials, interatomic potentials, towards some training data, which previously come from maybe experimental data, but nowadays mostly from density functional theory, DFT, or maybe more precise methods. But the question under investigations, once we have this, let's say, training data sets that we're discussing, let's say we have some potential functional form, which could be some classical one, maybe some advanced, which just has an umbrella term of machine learning potentials. Once we finish this potential fitting by different type of matching, and we get the interatomic potentials in here at the end, how reliable are these potentials and what we can achieve by using these potentials, how reliable would be this prediction. So here we have to distinguish between 2 concepts. One is accuracy, another is transferability. So accuracy is, let's say, the measure of how interatomic potential reproduce good training data, and transferability is measure of how interatomic potential reliable for the not yet seen, let's say, simulations. So in order to answer both of the questions, so we're also interested mostly in transferability, we would like to validate potentials. That's the main motivation of our project, and we do this validation by the comparison to reference data. But here I want to have a little bit step out and just discuss very few about the basic needs of atomic simulation community, where we can distinguish maybe 2 basic roles. One of a molecular dynamic simulation user, probably the person who use ready potentials and ready simulation codes. And the questions that they usually have in their mind is, what is the best appropriate potential for his particular purpose? What he can simulate with this potential, and how, and what could be the error of the simulations. Second role is interatomic potential developer, and so I wrote him a little bit orange, or to be honest, red, because this guy has a slightly difficult life because he has to develop potentials. It's not so easy task. And question which I have is how his new potential would perform. Is it any standard benchmarks which he can use to fit to test his new potential, and is it better than the previous one of his, or maybe some other previous potentials? So the first goal, maybe zero goal, basic goal, in order to achieve or maybe fulfill slightly this need of interatomic potential community, is data management. So what we could have in common in electronic and atomic simulations, it's basically very few things, but they're very basic, let's say, fundamental one. Sorry. Okay, I continue. As an input for atomic simulation, we usually get crystal structures like atomic positions. We also should have some interaction model, for example, density functional theory, maybe some meta DFT approximations, or the same interatomic potentials. And as an output, we get basically energies and forces, and based on that, we could get complex properties. So having this in mind, we also have to consider the given kind of situation on the market, let's say, and challenges. And of course, user tastes are different, and different communities has different way of doing this calculation. Someone does it in handmade way. Someone use some high throughput frameworks. Someone use external data source. It is listed here, but I think you can add after this workshop, I can add this to this list much more. Also, in each research group, we has a legacy data that was a lot of data that was obtained previously with or other old tools, and also question of security and restriction to the data, because not all data could go publicly immediately. Maybe we can use them for our internal scientific purposes, make publication only that, make it published. And so all these problems we could maybe group into several blocks, and those, let's say, data sources or data lakes as shown here. And what we need is to have some unified database, which could be on top of the iceberg, that would not replace completely the whole underlying data structures and data management tools, but it should contain only relevant information, reference to origin, and fine-grained access for security purposes. So, but that was the technical side, but what about maybe more scientific one? If we would like to navigate in this atomistic simulation space, abstract space, we could identify roughly three main directions, which is potentials or interatomic models. But in this axis, you probably could see that we also have experimental data, which also fills in this concept. So on the x-axis, we have prototypes of structures which represent atomic structures, of course, and that could be whatever you want and think, starting. But of course, in terms of atomistic simulations, when we know the atomic positions. And the third axis is the properties that could be achieved by combining interatomic potential and a given structure. And these properties, we can roughly divide it into three levels based on the complexity and time estimations. So the first level one property is the raw unstructured reference data, basically energies, forces, stresses, maybe volumes of the structure, if there are any. So level two properties is those which could be achieved for combining the previous one. For example, energy volume curve, elastic matrix calculation, phonons, surface energies. And level three is more advanced one, which is usually achieved in the large scale atomistic simulations, and which is not achievable by DFT. So that's the clear border between level two and level three is, can we achieve this property, can we compute this property by using DFT calculations in a reasonable time? So once we have this complex space, or I call it PPP space for prototype potential properties, we could start thinking about what kind of data types and how we should organize them in the context of the space. So, as I already mentioned, that the first entity is atomic structures, which basically contains crystallographic cell, atomic coordinates, occupations, symmetry group, if we have any. Then, of course, the basic level one properties is energy, forces, volumes. That's always should be presented in atomistic simulations, and the feature data, which depends on the more complex property, like you could have stiffness matrix or for elasticity, or you could have the phonon density of state, or for example, thermal expansion computed in thermodynamic quasi-harmonic approximation, etc., etc. So those those entities we could group into two type of fields in database. First one is a fixed field, which is always presented, and some arbitrary one, which depends on the considering properties, underlying properties. And of course, I know about the NoSQL databases and its benefits for some purposes, but on the other hand side, because we have a fixed predefined fields, why we could not switch to SQL in order to simplify manipulating with our data. And luckily, the PostgreSQL, not only this database, but now many others, allow you to store so-called NoSQL-like data types, for example, JSON or JSON binary, or shortly JSONB, in which will perfectly fit arbitrary fields, whereas on this predefined fields, we could feed all our very well-defined entities. So that's why we choose PostgreSQL as a backend for our database, because SQL and SQL is the best of both worlds combined in the database. And we would store in this database prototype structures, properties, and potentials, which I will show basically on this diagram. So we have a property-centric database, and as already mentioned, it could have some common entities or common relations. For example, property definitely should have a property type. It definitely should have a structure for which the property was computed in atomistic simulation sense, of course. On the other hand side, it should be clear by which computational engine or interatomic interaction model, or you can have different names for the same stuff, that property was achieved. So again, it's very, let's say, nice that we can also fit experimental data in this schema, because that's also the way of getting the property. So as I already mentioned, property is computed for some given structure, one or many. So this could be one-to-many relationship between structure entry and property. And the structure entry on its turn could be related to some generic entry or prototype. So here is an example. As a property, we could have some energy volume curves, which is, let's say, combination of 11 points with different volumes. I mean, 11 energy and volume of 11 structures with different volumes and corresponding energies. And because of this arbitrariness, this data would come into JSON-B field on this property table. On the other hand side, this energy volume curve compute, for example, BCC molybdenum, which is shown here. And this BCC molybdenum is just a particular, maybe, implementation or particular projection of some generic BCC prototype, which has no any chemistry, but just atomic positions and anonymous occupations. So this general entry is some general prototypes. Maybe some of you heard about some Strukturbericht notations, popular in Germany, of course, and so on and so on. And those group, let's say, subset of these prototypes we can combine into classes, whereas subset of structures we can combine into groups. But from topological point of view or from data modeling point of view, these groups and classes completely identical. On the other hand side, as already mentioned, we have a calculator type, which show by which underlying interaction model as property was computed, and we also can combine as an in-calculator group. So that's our data model. Now the first goal is interatomic potential validation, and as already mentioned, we would do this by comparing to the reference data. Of course, there is no ground truth, and we are not pretending to provide any ground truth. But for example, we know that majority of modern potentials were fitted to some DFT PBE or maybe other DFT data, whereas maybe 30, 40 years ago, the data source was mostly experiments, few experimental observations. So we would require to use this reference data. I mean, we can choose any of subset of properties as a reference one. We can do pairwise comparison. But here's the following complication appears. So how do we compare, for example, static property to static property when we have energy, forces, and stresses? That's pretty straightforward. We just take a difference between energies of, let's say, BCC molybdenum computed by WASP-PBE and BCC molybdenum computed by some MEM potential. But what about computing elastic matrix or phonons? There is a lot of sub-properties inside, and we require a separate receipt for doing it for each type of property. That's why we have a separate entity, which is called comparison type, which is, let's say, predefined piece of Python code, which actually stored in database. For purpose I will explain later, that implements this comparison by given to property of the predefined type. And when we apply this comparison protocol, if you want, we get a comparison entry which connect to original and reference properties. So that's why we have these two dedicated tables in here. So our general workflow looks like that from database. We get prototypes and populate it with composition. So we get initial guess for structures. I would say that for the moment we work only with Yury, and we have no any binary stringness, and so on. But the idea would be the same, except of the complexity of filling all the possible combinations. So once we get this original initial guess for structures with a reasonable volume, we can perform some atomistic simulations, start from full relaxations and doing energy volume curve for getting some property, and also precising of equilibrium volumes and doing some elastic matrix calculation, Fonon's vacancy formation, surface energy, and so on and so on. The key point here is that we should be able to apply this protocol of calculation of these properties both to DFT and to MD simulations. I mean, using, for example, lumps as a backend. So that we can say that our calculations was achieved with the same computational protocol. So they are comparable in this sense. And these properties go back to the structured database. And now we have the second round of comparison, so we can identify the comparable properties. Of course, it's not make sense to compare everything to everything, because mostly users choose as a reference experiment data if there are any, or DFT ones. So we, let's say, consider not all possible combinations in here, but when we have this, we get comparison protocol, get some property combinations, do comparison, enter, and put it back. And the second, let's say, third round is accessing this data for different purposes. So the first one is private access within our group with the Python interface, and for some data analytics or maybe development and validation of new potentials inside. I will show you example later. And another goal is what we start from the beginning is make a publicly accessible interatomic potential validation tools. So we have some visualization, comparison, and REST API, which is in our plans. So a few words about how we perform, for example, comparison of potentials and validation of them. Let's say for the given potential, we have its comparison to the same, let's say, some DFT data, but we have it for different type of properties. We have set of errors for predicting equilibrium volumes. We have set of errors predicting equilibrium lattice constant over different crystallographic prototypes, let's say, and we have to combine it all together. So because it's all even have different units, we could not put them in one loss function or in one score function, which will join it all together. We have to do the first comparison within each subset of the properties. And the second point that not for every combination of structures and potentials and properties, we could have successful combinations. So for some potentials, we could have more computation, for some of them could have less. We still have to deal with it somehow and provide as fair as possible comparison. So here we tackle this problem by so-called statistical approach, which called bootstrapping, and simple explanation is shown here. Let's say for on this x-axis, you have set of potentials, and each potential, each point in here represents, in that case, a deviation of equilibrium volume with respect to GGAPBE computed by WASP. And we have different set of points because not all calculations for not all structures was successful. So we can apply the bootstrapping, which means a selection with replacement, aggregate some subset of the fixed size out of this groups, and then we for each let's say iteration of this bootstrapping, we have our let's say collection of errors. We compute average, we compute median over them. So again, we try to preserve and be more robust with respect to outliers. So that's why we compute ranking, and we compute based on median values. And then we repeat this several times with the bootstrapping technique, and we have such called continuous ranking, which kind of shown here. So this technique, we believe, help us to get rid of some outliers, which could be the result of some maybe not converged or bad set calculation, and we could not control all of them due to the high throughput nature of this. So here I would like to try to demonstrate the website. So could you see my browser, I hope? So now it's running on my, let's say, workstation on Institute, and it's not publicly available, at least this version yet, but I try to show you very briefly the most common use case which you expect to have. So yeah, this is a website. So Now, as I already say, we have separation of different property types, crystal prototypes, structures, properties computed, and comparison of these properties. And maybe the main goal of all this activity is to provide to users a way of performing a potential comparison. So I just go directly to that. And for example, we interested in molybdenum. So again, only Yury is presented for the moment. Here's the property type which available in database for the molybdenum. Let's say I'm interested in energy volume curve and maybe elastic matrix, and let's say phonons for then the second another point computed by which potentials. Let's choose for the moment some DFT-PBE, VAS-PBE, maybe some AM Park for this, and I don't know, for example, bond order potential by Chuck. And we can also choose, take any of these prototypes or some part of them. Let's say I choose BCC because I know it's ground state for molybdenum. And I know that also A15 is the next to ground state. Usually it's considered in some researchers. Let me also add it to comparison. And I can take an overview, for example, of these properties first, then it will be just visualization. And in that case, we will see the properties which we choose. The first one was energy volume curve. So that's a visualization of energy volume curve computed by for different potentials and different prototypes. For example, A15, well, this is ground state, which reproduced all good by all potentials. That's not a big surprise. We can interactively see how this data distributed in different axes. So each point here again corresponds to some calculation. I can even click on this, and that will be data frame, data table representation. I can even go to the row property here. So it's a property page. This has a unique ID, name, reference to potentials and property types, representation whenever it's accessible, and also the raw data, which stored in this so-called JSON-B format, as we already discussed. And of course, this energy volume curve, as we can see here, it's a meta property, so it's constituent of several separate calculations. So that's a reference to related properties that was done, for example, A15 structures trained 1.08, and you can also traverse it and get the raw data for this one. But that's not the main goal. Main goal is to maybe select the potential. So I go back to my query page, select the same molybdenum, and now I just would be interested in all property type which I have in database, all potential and all prototypes, let's say, and I can just choose, let's say, PBE as a reference data. Let's see, yes, and now click on compare. Let's take a little bit of time. Yes, so that's exactly the that's exactly the comparison summary, or some let's say some of this continuous rankings that was achieved by different comparison submetrics. For example, this set of blocks is correspond to comparison of energy volume curve, or this set of blocks correspond to comparison of phonon properties, and width of this block say you the median average rank for this property among different bootstrapping iterations. So we can say that, for example, WASP LDA is the most close to WASP PBE, which is not a big surprise. But the next to this is Go minimum park potential, and then Go ADP Starikov, and so on. But we can even go for more details about each of this comparison. Let's say I'm wondering why, what about elastic properties? So here we could have, again, as I said, each property, atomic property has its submetrics, sub-properties. For example, for elastic matrix, we have stiffness matrix, but out of this we can get shear modulus, bulk modulus, Young modulus, and so on. So this is shown as here as a submetrics, and you can see this error matrix. And here we could see a representation of this error matrix with, for example, that's some aggregate statistics of the let's say errors for comparison. Let me choose one of this point, for example, maybe A for diamond. And here we have this entity which I discussed before, is comparison entry. So this one corresponds to a result of comparison between property number this and number that, which is reference one computed by PBE as we asked, and as, for example, last day as we click. And that was done for the common prototype and common composition. And here we have a submetric, so comparison values. You see a lot of them, but we show only those which is highlighted and has weight more than 0. And of course, we can traverse this property. Maybe I can choose something interesting. I don't know, for example, let me try to click this one. Let's say we now want to, okay, now we decided that park potentials, after all, looking at the tables is the best one. So we go to this page, and so nothing interesting in calculator settings, but we have links to its original one that was taken from, for example, NIST interatomic potential repository. I would say that majority of our potential that we're testing here was taken from the OpenKIM database and NIST interatomic potentials repository, because we want to have the, let's say, permanent links to the potentials that user can go and take this potential if he decided that it is good one. But let me go back to my presentation and quickly jump through it. So the second goal that we can achieve by our data management structure is interatomic potential development. So briefly speaking, in a typical framework workflow, we have a reference data, choose interatomic potential form, do the potential fitting, and model validation. So with this data infrastructure, we can fulfill both ends of this workflow, and this feedback loop by the developer. We also would like to make it as easy as possible. So for example, this is a snapshot of our interactive Jupyter notebook, which was used by my colleague Alberto Ferrari when he developed one of the bond order potentials. So he had immediate access. Once he had some intermediate version of potential, he can run the test, for example, set of energy volume curves here for 200 of random structures, and immediately see the error distribution and maybe make decision about adding some of the structures to this fitting. Another example is fitting of angular dependent potential by Sergei Starikov, and he asked me just do a quick validation of his new tested potential with respect to his old one that was done in 2017, and with other potential which he likes, and just to compare how different metrics looks and how his potential looks with respect to other interatomic potentials. And of course, as a future perspective, we can go further with this scheme, and we can add automatic or AI guided control in this feedback loop, but that's another story. So the future perspective is the distributed resources. So we pretty much thinking in the same way of standardization as you in Optimate community. And if we go back to our need of interatomic potential community, we have different roles like users and potential developers. For users, we can fulfill the access of interatomic, for storing of interatomic potentials, which is achieved by NIST, IPR, OpenKIM, and other projects, whereas the model validation also could be addressed by most of these resources, and provides the new interatomic potentials that also could be addressed by all these resources, which is not yet fully done and should be done, is exactly what I was showing before, is the standard validation protocol. So we want to give to the users, especially interatomic potential developers, a standard way of estimating his potential with some standard sets. And also because it's a distributed sources, possibility of providing new data, validation tests, resources, protocols, and so on by new interatomic potentials data provider, which is very similar to, I think, Optimate data provider in your concept. And of course, in easier world, all should be done and accessible through the REST API, maybe some Python APIs and web interface, so all three at the same time. And the typical workflow, for example, using REST API with interatomic potential developer is the following: that when he had his interatomic potentials, probably because I asked several people, interatomic potential developers, none of them would be agreed to upload his not yet finished work to some extra servers and do some validation in there. So of course it should be so-called end calculation. So it should be all possible to do on user's personal machine, just giving him a data like a standard DFT data or standard comparison protocols, or maybe standard comparison properties for validation. That's why it's crucial to provide this unified interface. And as a proof of concept, that's just a few lines of code which show how should be possible to have this access by the potential developer to our web platform. So he can query some crystallographic prototypes, radius structures, computed properties, or comparison protocols. And but the following question is still open, and it's a lot of work, I think, to make it to answer this. What about data consistency? So once this some queryable API is accessible by database, we were very interesting to compare how it's how different how the same properties computed by the same potentials for the same structures would be predicted in presented in different databases. So, for example, here's a query of elastic constant for FCC aluminum, especially C11 constant of the stiffness matrix, and you see that in OpenChem database and our database, it's very good matching except of one potential in here. And when we start to try to understand why it happens, that happens probably due to the underlying algorithm, how this property was computed. So when we compute elastic matrix, we would require to do some deformation of the structure, and this strain range could differ, and that is in principle choosable by should be chosen by user, but if we choose some value, we can get some, it depends on the values that we choose, we can get different output values, let's say. And this is some numerical experiment. If we do our numerical, let's say, derivatives with different strain range, we could get different C11 values. And of course, that's good if you, I think we're lucky enough that we choose our value here on this plateau. But let's bring, maybe raise up the following idea. What about the properties calculation protocol? So I think it's something which even more complicated to answer than what is the common standard for access the data. But if we think about how we usually compute our data, our properties atomistic simulations, so we get some initial structure, we perform some deformation sets, and maybe we just do straightforward optimization with built-in tools. Then we do post-processing of this data and get meta property. For example, combining set of deformation, we can get elastic matrix, or combining set of forces estimated by atomic displacement, we can get the phonons, and so on and so on. Or sometimes we could have a more complicated workflow, but I think that depending on the tools that you use for computing this, on one hand side, we could have maybe a lightweight AEC, and you can compute some kind of properties. On the other hand side, you should have persistency, and when you do long-term DFT calculations, and you could use some fireworks with Automate or AIDA or Aflow or Pyron, which we're actually using. So it's really crucial to make the separation between so-called scientific logic or business logic, how it's called in computer science language, and the underlying technical details, which I call computational engines. And the separation between them is really needed for unification, probably, of the way how do we get these properties. Just very brief idea how we can get it is to make the separation, we require some unified language to describe atomic properties calculation protocol, which could be mapped to different execution backends. So one of the examples from deep neural network one is, let's say, Keras with a high end, which allow you to construct some neural networks, just combining layers, and you have underlying backend, which could be TensorFlow or Ocean, or maybe something else. The same probably is required in here. And here my concluding remarks. So we had some specially designed data management system, which get populated by high throughput atomistic simulations, mainly done by Pyron, but also with a lot of AC simulations, calculations, which require to also support the legacy simulation data which we have, and maybe importing some external data sources sometimes. And the goal for this is new interatomic potential development, validation, and provided as a service for community through the atomistic tools portal. And as another repetition of the same idea, that separation between atomistic simulation protocols and actual computational engines is required for unification. Yeah. With that, I would like to thank you for your attention, and ready to answer your questions.